So let's continue our discussion on the physics of many electron atoms. This is a big business. Today we are going to discuss something that opened up a big field. Basically, if you follow today's lecture, you know about 60% of quantum chemistry. And then all the ideas here also can be transferred to the physics of molecules. So we will hit at some important concepts. The goal in our course is to introduce the ideas, the concepts, because the calculation in full interacting electron system are very difficult to do. So the idea is to introduce the concept. Maybe someday in your project work, postgraduate study, you have some numerical package to do such calculations. At least you know what are involved in these programs. So we did a lot of hydrogen atom plus a little bit of things. That is a very good place to learn all the details in atoms. So hydrogen is like the playground to learn the details of an atom. Another playground is helium atom. So today, after introducing the general many electron quantum mechanics problem, then we will move on to see how we can use our tools, perturbation, variational calculations, to understand some physics of the helium atom, especially the helium ground state. It turns out that if we understand how to handle the helium atom ground state, that will open up many important concepts. And actually, in practice, those concepts become real calculation tools. And then I think most of the people doing theoretical chemistry are doing such calculations. So let's get down to business. Last time we were on this page. This box gives us what is the Schrödinger equation. So this box gives us what is the Schrödinger equation of a Z electron atom. So let's recap how to write down the Schrödinger equation. So we have this kinetic energy of Z electrons. That is the kinetic energy term of the Hamiltonian. Then every electron sees the nucleus. The nucleus has plus ZE charge. Electron has minus E charge. Thereby, we have this Coulomb attractive potential energy functions. The term that is hurting us, making the problem insolvable, is this electron repulsive Coulomb potential energy term. So first of all, there's a plus sign indicating that it is a repulsive potential energy function. Then it is E squared divided by the separation between two electrons. There are many pairs of it, but countable. If you have Z electrons, the distinct pairs are a total of Z times Z minus 1 over 2 pairs. So that is the total repulsive electron interaction potential energy term. So thereby, we know the Hamiltonian and H psi equals E psi is the Schrödinger equation. Now notice that first of all, this E is now indicating the allowed energies of the whole atom consisting of Z electrons. At this point, there's no idea about electron number 1 doing this, electron number 2 doing that. It's not such a physical picture. The E here refers to the whole atom. So after we solve this, if we can solve this, E represents allowed energy of the atom as a whole. Then the point is, we know the governing equation. So this box is the governing equation for any atom. From helium, Z equals to up to uranium, Z equals 92. Those are the atoms that we can find naturally on Earth. The periodic table is longer than that. I think it's now up to 118 or 119. I mean element 118. But beyond 92, those are short lifetime atoms. We can make it in a lab, but on Earth, naturally, you cannot find a place where you can dig out such an element or their compounds. All right. So the point is, we know the physics, we know the governing equation. Second point, we cannot solve this equation. Now I would like to explain some new physics about multi-electron atoms. The first thing you saw in the equation is this stationary states of a many electron atom. Notice that it is a function of the coordinates of all the atoms. Now, it is very different from a function of one electron's coordinates. What do I mean by that? This wave function is about the whole atom. There are Z electrons, thereby it is a function of Z variables. This is called a many electron wave function. If you are working on other things, well, in a nucleus, you have a lot of protons, neutrons. That is also a many particle system. More generally, it is called a many particle wave function. But we have electrons in the atom, so it is a many electron wave function. In an abstract sense, if you don't like wave function, you like the Dirac abstract stuff, this is a many particle state. So this Schrödinger equation is to solve for this many electron wave function. Now, this is in contrast to the hydrogen atom, where you have a very simple wave function of x, y, z of that one electron in the hydrogen. That is called single electron wave function. Now, the point I would like to make is the following. So generally, for a n particle problem, n electron, Z electron, for example, then you have this many particle or many electron time-dependent Schrödinger equation. The Hamiltonian is exactly the box. H psi is this part, okay? And this is the general many electron time-dependent Schrödinger equation. And when you do this standard stationary state procedure, then you get our Schrödinger equation, which is the time-independent Schrödinger equation. So now, let's have a general idea about this many electron wave function. What is the interpretation if we can solve for it? Many electron is too complicated. Let's consider two electron case. So we have psi equal is a function of R1, R2. So we have electron number 1 in the first coordinate, electron number 2 in the second coordinate. All right. So now, what is the meaning of it? Again, we are using Born's interpretation, but it is extended to many electron states or many electron wave functions. So what does it mean? We have this psi square, psi star psi, but now we have 2 electrons. Thereby, we have to, there are 6 variables. X1, Y1 is Z1, X2, Y2 is Z2, because we have 2 electrons, say in helium. Now, we need to involve 2 volume elements. One is for electron number 1, another is for electron number 2. So the physical meaning or interpretation of this wave function is as follows. Psi square, this is this thing, times 2 volume elements, d tau 1, d tau 2, has the following interpretation in quantum mechanics. It's the probability of finding particle number 1 at R1 in a box, in a tiny box, d tau 1, and particle 2 at R2 in a tiny box, d tau 2. So you see, it's a very natural generalization of the Born's interpretation of a single electron wave function to a many electron wave function. But when you have 2 particles, there is one big question left. We will have more discussion on that later, but I would like to bring this out at this point. If this particle number 1 and particle number 2 are indistinguishable, indistinguishable is called 不可分辨的, 不可分辨的. It is, I think, more stringent than identical. Well, electrons are identical, no doubt. But I would say, if I have an electron here and another electron on the moon, from their location, I can still distinguish them. Indistinguishability means identical particles living close to each other in the same place. So 2 electrons living in the same helium atom, then we have to think about this footnote. So when you have 2 particles, 2 electrons, they are indistinguishable, then we have to think about whether they like each other or they don't like each other. We know that, well, later on you will know that, bosons tend to like each other, fermions tend to dislike each other. They want to be slightly farther away from each other. And electrons are fermions. They don't like each other. And in that case, the wave function will have to obey some stringent requirement. It is about the symmetry when we interchange the coordinates of 2 indistinguishable particles. Nonetheless, what we are discussing here, the interpretation remains the same. That point has to do with how to write down a proper wave function when you have many electrons. So this box is optional. We don't need that for the remaining study in our course. But some of you may be going into advanced statistical mechanics, hydrodynamics, things like that, and that is somewhat related. So extending our discussion from 2 particles to n particles, the interpretation following Bohr's interpretation would be, this is the probability of finding particle number 1 here in a small box d tau 1, number 2 here, R2, small box here, and so on. Okay, no doubt. Thereby, there's a normalization. So you integrate over all the n electrons coordinates over all the available space. These n electrons must be found somewhere, right? So add up all the probability. That is the normalization of many electron wave functions. Now, an interesting thing here appears is that how about we integrate over all volumes of particles but one? That is to say, we integrate over, for example, from particle number 2, 3, all the way to n, but not integrating particle number 1's coordinates. So after you do all this integration, this is a function of R1. In general, if this is a wave function, is a function of t, we still have a function of t as well. So this is called P1, and that is the position probability density. That is to say, I only focus on one particle, say number 1 here, and I don't care, independent of the positions of all the other particles. That is to say, you integrate over all the rest, and then I focus on one particle, and that will tell me if I want to look for this particle number 1, what is the probability here, there, and I don't care about what happened to the other particles. Now, this P1 is useful in more advanced statistical physics studies. Another one that is important is the two particle correlation. That is to say, you integrate over all but 2 particles. Usually, if you work out the statistical physics of P1 and this Pij, you know a lot about the system. Okay, now that is just an optional page. We are not going to use this later. Now I would like to make the most important point about the general problem. The point is it cannot be solved. Very simple. Okay, but why? The term that kills the problem is this term. This is the electron-electron interaction term. Why does it kill the problem? It is because it cannot be separate. What do I mean by that? Now you may try, but don't spend too much time. See if you can write this as some function of Ri and then some function of Rj. If you can write this thing into a function of Ri only plus a function of Rj only, then according there's a question I will answer that later. If you have a function of Ri, Rj, okay, and that is this function, if you can separate into a function of Ri only and a function of Rj only, then you can make use of the separation of variable techniques. You can separate the many electron problem into electron number 1 problem only, number 2 only, number 3 only, and so on. Then you can do it very leisurely because all of them are single particle problems. Okay? Now, look at this very ugly thing. It is 1 over Ri minus Rj. You cannot do such a separation. Thereby, you cannot separate it into functions. Okay, so Mr. Choi, I already answered your question. It's not about matrix, it's about functions. So if you cannot separate into it, you have a real many body problem. Okay, so it is this term that make the problem a real many electron problem. Okay, now so below here I make an assumption. If this term disappears, now that is a big if, we cannot do that. If that term is not there, then your Schrödinger equation with the Z electrons actually is of this form. Okay, what I'm saying is this. If this term is not here, okay, then I can take the R1 kinetic energy with the R1 potential energy and then group it into one bracket. Similarly, the R2 kinetic energy, R2 seeing the nucleus potential energy, group it. Okay, so if you do it for every electrons, you have this simplified Schrödinger equation. Now, immediately you see, this is a Hamiltonian concerning R1 only, R2 only, or Ri only. This is a separable problem. Then you go through separation of variables. The wave function, write it into a product of single electron states. You substitute this into here, go through the argument of separation of variables, then you will end up with Z single electron Schrödinger equations. Okay, you can solve every one of them. And then the allowed energies of this total Hamiltonian is the allowed energies of each particles and sum them up. I hope that you know this argument of separation of variables. I will summarize it in very short phrase. The wave functions, the single electron wave functions multiply is a product, right? And the total energy is a sum. That comes out from the separation of variable exercise. So the point I try to make is the following. If this term is not there, the problem is solvable. But if we include this term, the problem is not separable. Therefore, you have to think about some ways to approximate it. Very difficult to do. Okay, so here I just remind you of separation of variables, but I would not go through it here. You should have done this several times. For example, the R theta phi problem in hydrogen, you separate into the radial part and the theta phi part and solve them separated, right? So the point is, this is the take-home message. When you have this Coulomb repulsive term between the electrons, it is a real many electron problem. The wave function should be a function of all the coordinates together. Okay? And it cannot, in principle, be written as a product of some single electron states. It cannot be done because of that it is a real many electron problem. Okay? So this is the main message up to this point. Any question here? Up to now, I just want to bring out this many electron atoms from helium on. It's very difficult to do. Indeed, we are going to do some approximation. So far so good. We will try everything we can, but approximately. All right. So do you get the point? If this term is here, okay, this cannot be written as a product of single electron states. Okay. So what to do? Okay, either we give up, go home, wait for the final exam, or we move on to do something using the approximation tools in our toolbox. Of course, we have the whole subject of chemistry. They are playing with atoms and molecules, and they use a lot of single electron ideas. They still use 1s, 2s to be those single particle states idea throughout the whole periodic table. What are they doing? That is the remaining part of the discussion. So we will make some approximation. In particular, we just said that we cannot do that. And then a few pages later, we are going to do that. We will make it equal. So that is at best approximate. Therefore, we will try to approximate a many electron problem of the atoms into the wave function into a product of single electron states. The remaining question is, how can we make good approximations to get this single electron states? Can we still realize something called 1s or 2s in helium? In principle, not, right? Because 2 electron wave function phi of R1, R2. That is the right thing to do. Okay. Nonetheless, I just told you that not true, strictly speaking, but then we are going to make this approximation. That's very often the situation. You first realize what is not allowed in principle, then when you step into that place and then you say, I'm going to make that approximation, and then see what happens. So what is the way out? First idea is that we want to save, to rescue the picture of single electron problem. So all in all, we want to make use of the knowledge that we know. If we can invoke some single electron states, in particular make approximation that an electron is living in some strictly symmetrical potential, then we have all these solutions we can make use of, and then we can fill the electrons into this single electron states. So we have some idea now. We want to reduce the problem into single electron problems. So when we focus on one electron, there are Z-1 electrons remaining. Can we possibly include their effects into an effective potential energy function that the single electron feels? So at the end, we hope to do something like that. A single electron that we want to focus on, there is a potential energy due to the nucleus, plus there's another repulsive potential energy due to Z-1 electrons. Therefore, if we can do that, the problem is reduced to solving a single electron Schrödinger equation. But there's a remaining question. If we can do that, we have Z electrons. What is the rule to fill that those electrons into the states that we solved? That has to do with something related to Pauli exclusion principle, but more generally, there is a regulation about the symmetry of the wave function. So these are the 2 points that we want to develop along the way. Now we get our hands dirty, okay? So the general discussion ends. The general discussion means from helium to uranium. But then we pick the simplest case to start with. The simplest atom is to consider helium. So let's write down the helium atom problem. 2 electrons, okay? Now let me tell you one more time the storyline. In learning all this spin orbit, relativistic effect, if you understand hydrogen, basically you can apply what you learn to other atoms. Then when you move on to many electron atoms, if you understand the helium atom physics and the techniques, then you know how to move on to other many electron atoms, okay? So that's why we will focus our effort on understanding the helium atom physics. Let's write down the Hamiltonian. There are 2 electrons and 1 nucleus. I assume the nucleus to be fixed at the origin 0, 0, 0. Don't worry about that. And then I have electron number 1 somewhere with the coordinate R1, electron number 2 with the coordinate R2. Their separation is this R1 minus R2. Thereby, the Hamiltonian is a 2 electron Hamiltonian. Electron number 1 kinetic energy, electron number 1 sees the nucleus. Electron number 2 kinetic energy, electron number 2 sees the nucleus. These 4 terms are still representing a non-interacting system. You see the 2 brackets, one has to do with electron 1 only, one has to do with electron 2 only. I use a small h1, h2 to represent them, okay? Now, the term that kills the problem is this electron-electron repulsive potential energy, okay? So, as we discussed, these 2 terms only, each one of them is hydrogen-like, not exactly a hydrogen, but like a hydrogen, because the nucleus now has 2 times the charge of hydrogen. There's an extra 2 here. Nonetheless, it's the same mathematical problem. We can solve them. So this part together is a solvable part, all right? Now this term makes the problem insolvable. So what comes to your mind? We can take this as the unperturbed problem and then do this in first order perturbation. That is at least the first thing that should come to your mind, right? And we will do that. But for the moment, let's try something dirty, right? Now, first of all, let me remind you, the helium atom problem is this Schrödinger equation. This is a real many-body problem, 2 electron problem. That is to say, the wave function in principle cannot be written as a product of single electron states. This is not true, strictly speaking. But we want to set up the stage to make approximations. The first thing that comes to mind is this: the first 2 terms that can form a H0 in our perturbation setup. So if we take this, then we have the solution of being a product of H1 solutions times H2 solutions, right? So we have electron number 1 in some single particle states, it obeys this H1. Electron number 2 in some other single particle states, it obeys the Schrödinger equation defined by H2. When we do that, this is, if we make this approximation to the full helium atom problem, then it is a first step, okay? And then if we only look at these two parts, then the energy adds. So this is the separation of variable arguments. So here, I would like to write down what we will be using in the following pages. On the right-hand side is a reminder of your hydrogen atom problem that you solved last term. We have this Hamiltonian for hydrogen. This is the Schrödinger equation. Let's look at the ground state. This is the ground state wave function. And this is the ground state energy. A0 is the Bohr radius. And this chunk is minus 13.6 eV. Here, I would like to introduce a new measure of energy. Let's define some funny thing called 1/2 tree. That is an energy. What is it? It is 2 times hydrogen ground state. 2 times 13.6. Okay? So basically, we place this by 16. That is the definition of 1/2 tree. In other words, hydrogen ground state has the energy of half tree. Half tree is a very commonly used unit in atomic and molecular physics. It belongs to a system called the atomic units. I have an appendix, 2 pages about this point. Basically, it's the following. After you solve the hydrogen, you have a length scale, Bohr radius. If you measure distance by the Bohr radius, and then you have an energy scale, which is the hydrogen ground state. But for the purpose of atomic physics, it's better to define something called 2 times the ground state energy. That is 1/2 tree. So you measure energy in half tree, you measure distance in Bohr radius, and then 4 pi epsilon 0 is 1 unit, etc. That is the atomic unit. For our purpose here, I just would like to define this energy scale. So this is minus half tree. So on the right-hand side is something that you know. Last term. Now look at our single electron problem H1. The only difference is this 2. Okay, so I have this 2 here. This is why it is called hydrogen-like. In fact, you can solve a hydrogen-like problem by inserting a Z here. Okay, so you can repeat the hydrogen problem by inserting a Z here and then solve them all the problems again. The solution is something that I listed here for our purpose. If it's a Z here, then the ground state becomes this form. So hydrogen has Z equals 1. That's why you have a 1 here. Okay, and then Z equals 1, you have a 1 here. All right. Now, this is for Z general. Helium has Z equals 2, the 2 here. Okay, you plug it in. So helium has this ground state form. In terms of ground state energy, because the nucleus has twice the positive charge and the energy is related to nucleus attracting the electron. So therefore, there is a Z square in front. So for helium, Z is 2. Therefore, it is 4 times as stable. Okay, for this particular problem. Therefore, it is 4 times half Ha3. So it is -2 Ha3. Okay, so that is the problem solved already last term for our H1 problem. The H2 problem is identical. See this? Only for the second electron out too. So therefore, this part, we really know the solutions. The wave function ground state of H1 and ground state of H2 multiply. And the energy add to each other. Okay? So separation of variable argument. So therefore, we take the solvable part. The ground state energy will be -2 Ha3 plus -2 Ha3, that is -4 Ha3, and it is -108 eV. Your Ha3 is 2 times 13.6, okay, 27 something, okay? So times 4 is about 100 something. So this is ignoring the interaction term. Therefore, we are ignoring at the moment, ignore this term. And the ground state wave function multiply. So we copy the ground state wave function for the hydrogen-like part, another hydrogen-like part, but one is for electron number 1, R1, electron number 2, R2. Okay, so I copy the wave functions, multiply them together. The first expression, I keep it into Ez, but helium problem here, Ez is 2. So I plug in 2, that is equation 15. Okay, so at this point, we see that we have 5 terms in our problems. So 1, 2, 3, 4, 5. If we ignore the interaction, electron-electron interaction term, the first 4 terms do not cause us any trouble. It is a solvable part. The solutions, well, focus on the ground state, very humble. So the ground state energy is this. The ground state wave function of this part only is these 2 expressions. Okay, so we are making progress, but don't be too happy. The real problem is there is a 5th term. So the first 4 term is exactly solvable, but with the 5th term interaction term, the problem is not exactly solvable. So let's see how bad we have been doing ignoring the interaction term. So what we got is, if we only take into this part, solvable part, ignoring the repulsive energy, then we predict the ground state to be of this number. We look up tables. You can Google it now, helium ground state energy. You will find this -79 eV. That is taken as the actual value. So we are off by 30 eV. Pretty bad, huh? Well, depending on your taste, I would say not too bad, okay? But 30 eV is a big energy. So we have more work to do. First thing, we cannot ignore the repulsive term. But secondly, a good sign is the following. What we predicted is more negative. So what we did is that if we ignore the electron-electron interaction term, we predict this helium atom to be too stable when compared to the actual value. But it's a good sign in the sense that we know if we include the positive repulsive Coulomb energy, repulsive means positive, it will bring this value up because it's positive. This is negative, you add some positive value. The only direction it will go up is to go up here, right? So maybe it's still possible if we do some approximation, first order perturbation, for example, to calculate what is the expectation value of this when the unperturbed wave function is that. Now, can you imagine there's an integral? E squared over this R1 minus R2 in the middle. This thing on the left, this thing on the right, and two integration. Because we have two particles, we have to integrate over x, y, z of R1 and x, y, z of R2. It's a 6 integrals. Do it, it is an energy. And it is going to be positive. Thereby, it will push the energy up. Will it get to very close to that energy? We have to do the calculation. Okay? So there is a few pages later that I will tell you the answer. If you want to know how to do the integral, the TA will do the integrals for you this week. It is a 6, I don't know what to call it, multiple integrals, okay? There are 6 of them. You have to do that. And it turns out that can be done. That can be done, I mean, that integral can be done analytically, okay? So that will be one way forward. So let's take stock before we start doing approximations. This is the problem we are looking at. At this point, we are doing something very humble, ground state energy, ground state only. In principle, we cannot do that due to the presence of this term. This is strictly speaking. But as a physicist, when we see that something cannot be done, we will do it anyway. So we will try to approximate it this way. But when we do this, you must understand this is at best an approximation. But then we are going to do this. Then the remaining question is, how can I make reasonable approximation so that this is not too bad? Okay, therefore the question is how to find these single particle states. What are they? How can I include this very troublesome term into the calculation of the single particle states? Then what is the rule of putting the two electrons into the single particle states? The Pauli exclusion principle. So after we do that, the idea that comes out is that we will be doing something called the independent particle approximation. And more profoundly, we will introduce an important concept about self-consistent mean field approach. The famous name under this method is called the Hartree method or the Hartree-Fock method. If you buy a numerical package to do such calculation, you pull down the menu there, then immediately you will see Hartree Hartree fork, self-consistent thing. But I hope after this discussion, after this course, at least, if you have that numerical package to play with, you know what you are choosing, okay? So at this point, let's take a break, and then we will start the perturbation calculation.